In this video, we are going to derive the electric potential due to a point charge. And so basically in this setup right here, we have our point charge, which we're going to call capital Q. And basically what we want to find is we want to find the electric potential at this point at a distance r away from our point charge. So we're just going to say that this is basically our test charge, which we're just going to call positive lowercase q. But actually, it doesn't really matter what this charge is, right? I'll show you. Basically, we know that the electric potential for this test charge, basically if we recall, electric potential is denoted by the symbol V. Electric potential is basically just the electric potential energy of our test charge, which is U, divided by the value of our test charge, Q. So that's basically what we would have. And so you might be thinking, as we increase the value of our test charge, we should expect a decrease in the electric potential. Because we're increasing the value of our denominator, we would expect our electric potential to decrease. But that's not what actually happens. Electric potential will actually remain constant. Because as the value of our test charge increases, so does the electric potential energy. If you recall, electric potential energy is K capital Q lowercase q over R, right? In the case of this setup right here. And so really, notice how as the value of our test charge increases, the electric potential energy will increase proportionally to it, because as you can see, electric potential energy and the value of our test charge are proportional to each other. And so that's the idea. So basically Q increases, so U increases, electric potential will remain constant. So, well, here's what we're going to do. Basically, if our test charge doesn't matter, it turns out that electric potential only depends on the value of our point charge and the distance away from our point charge. That's basically it. And so here's what we're going to do. Basically, notice how we could just take what we have for electric potential energy and substitute it into here. Right? Because this is the same thing as U, because they're equal to each other. So we could just substitute that in. And so when we do that, here's what we're going to get. Okay, so substituting in electric potential energy for K capital Q lowercase q over R. Right? And we're dividing this by lowercase q. So this is what we have. And so you can already see from this that lowercase q cancels out. And so because lowercase q cancels out, it's completely gone now. And so really, it does not matter what this test charge is. It does not matter what the charge is at this point. The only thing that matters is the value of our point charge and the distance away from that point charge, as you can see from what we get here. And so simplifying this, we can now see that electric potential is just K capital Q over R. And so this right here is the idea of electric potential. And so this is basically the idea. Electric potential is just KQ over R. Now, unlike electric field is a vector, right? Well, electric potential is a scalar, right? Because really, it's dealing with energy, which is a scalar, and charge, which is a scalar. So really, this right here is a scalar, and so we're not thinking about direction when it comes to this. And so when we're evaluating this, we aren't thinking about the magnitude of our point charge. It's just the value of the point charge itself. And so the idea is if our point charge here is positive, then our electric potential at this point would be positive, right? Or just any point, right? And if our charge is negative, then electric potential would have to be negative. And so that's the idea. This is basically what electric potential is due to a point charge, and that's pretty much it.